Okay, we're going to continue talking a little bit about our experiment that we just ran to find out that taking classes online is less good than taking classes in person. Now, one of the questions you might have is, well, why are we taking online classes? And the answer is we're taking online classes right now because there's a virus that we need to slow the spread of and allow for a vaccine to be developed so that we can be healthy and with each other again in normal human times. So there's a real good reason why, even if this is right, even if online is less good, we shouldn't just waste our time and sit around and wait for a virus. We should at least do this, because it's not like there's zero utility to online. It's almost as good. The effect that online versus face-to-face has is called the effect size. So if we know that there's a difference between a dependent variable based on changes in an independent variable, the next question is, well, how big of a difference? So, if I'm thinking about differences, some differences people don't like, for example, women have higher IQs than men. You don't like that because you want everybody to be equal, and it's not true. Everyone's not equal. And women have higher IQs, or, score higher on standardized tests of intelligence than do men. They also earn more college degrees, more doctorates, more MDs. They're dominant in the academics and scholarship now. But, we get to pee standing up. No, I'm just kidding. The difference isn't that big. So, if you consider all of men's IQs, it's a normally distributed, here, let's zoom you in there. It's normally distributed. If we consider women's IQs are almost the same as men's, except they're a little bit higher. So you'll see the difference between these two is negligible. It's a tiny difference. And interestingly, they have a different shape. So there's more than just are two things different. These two giant, all men and all women's IQs, that's a huge population. The shape of them is different. So, in fact, women's is more leptokurtic, men's is more platykurtic. What do I mean? Leptokurtic means that there's very little variability in a distribution. Platykurtic means that there's wide variety in a distribution. Think of a platypus. I don't know how to draw a platypus. Here, I'll make him Perry the platypus so you guys recognize him. Platykurtic is something that has a wide variability. Leptokurtic has narrow variability. Effect size describes how much of a difference between two populations does an independent variable make. The independent variable here is male or female, and we're measuring IQ on both, and it turns out females have higher IQs on average than males. Does that mean that if you see a woman you just think she's a genius? No! Here's the weird thing. Because of the platykurtic nature of a male IQ distribution, it turns out we have more geniuses that are male. Also, more people who have intellectual deficits that are male. Females' curve tends to have less variability, and the average is higher than the male's average. So when you hear somebody like me say something that says women are more intelligent than men, you can't say complex things about people that are that simplified, because there's far more to it than that. Again, why do we have more geniuses that are male than female? Because the distributions are different. They don't even have the same variability. But if you hear something, and this is technically true, the average female's IQ score is higher than the average male's IQ score. Makes perfect sense. That's true. But that doesn't mean that you generalize and go, oh, all women are smart and all men are dumb. No, no, no. Half the world has IQs above 100. Those people are considered generally intelligent. Half the people in the world have IQs below 100, and those people struggle with intellectually difficult things. You're a college student, and so guess what? It's much more likely that you're on that side of the curve. See, there are differences in people. People that attend college classes, or in this case, take online college classes, tend to be in one position in this distribution. Hold on, my wife's going to work. I'll be right back. Okay, so you want to know how to figure effect size. A guy by the name of Cohen figured out that effect size was very important. Instead of just chasing statistical significance testing and saying, okay, this makes a statistically significant difference, Cohen asked, well, how big of a difference does it make? And that turns out to be a much more important question, whether or not we should pay attention to the fact that there are differences. Let me give you an example. Let's say I've made a new sports hydration drink, and this sports hydration drink, I'm going to name it Statserade. Not to be confused with the trademarked and copyrighted other sports drink. This sports drink will reliably make you more hydrated than drinking water alone. You take my Statserade drink and you will get more hydration. Are you willing to pay the $1 for my Statserade? That really comes up with the question, well, how much more hydration are you going to get with Statserade than you would drinking water alone? Okay, I'm going to show you. Here is Statserade hydration. Here is drinking water alone. Now, you see that difference is too small for it to be really worthwhile in drinking Statserade because the effect size is tiny. Right? They both have the same sort of shape. The distributions have the same shape, but the difference between them is minuscule, right? Yeah, Statserade does make you more hydrated. I put a pinch of salt in a bottle of water, and I call it Statserade. And it reliably makes you more hydrated, but just by a smidgen. So the effect size is so small that it doesn't really make a big difference. So here's what we see. The mu for water is, let's say, 10. The mu, this is for Statserade, is 11. And since they both have the same sort of standard deviation, the standard deviation is 2. I'm sorry, 12. It's huge. Huge standard deviation. So if we have Cohen's D, we'll have D is equal to mu1 minus mu2 divided by the standard deviation. So here we would have 10 minus 11 divided by 12. In that case, you've got 1/12. That's a really small effect size. So how do you know how big an effect size should be? Well, the effect sizes that we consider to be large, Cohen said, are something on the order of 0.8. So if it's up at 0.8, then that's a reasonably large one. If it's at 0.2, it's a small one, and if it's at 0.5, it's kind of a medium one. So Cohen's effect size ratings, small is 0.2, medium is 0.5, and large is anything above a 0.8. And the ratio of these is like, okay, if the difference between mu1 and mu2 is so big that it's almost a full standard deviation, that would be a really large one, right? Because it's the ratio of the difference to how big the variability is. This is Cohen's D and effect size. Okay. Statserade does reliably make you more hydrated, like 1 milliliter more hydrated than water alone. It's got a little bit of salt in it. What scientists call electrolytes. And if you really needed that extra milliliter of water, let's say you were dehydrated, you know, they rescued you, you're so dehydrated you might die. Then it might be worthwhile to drink the Statzerade. But in all other situations, right, because you have to pay $1 for it, whereas it's free otherwise, right? Water's water. So in a situation where you had to have as much as possible, sure, you might pay for that extra milliliter of hydration, but for the most part, because the effect size is so low, even though it's reliably a difference, even though it's reliably better and more hydrating, it's almost like you don't need it. And so Cohen really focused psychology on saying, okay, yeah, we could go and search for all these different things that make a huge difference, but if they don't make a huge difference, should we really spend our time working on that? And that's what Cohen brought to psychological psychology, is the idea that effect size is going to be very important, not just statistical significance testing. Next thing we'll talk about is power. Before we get to power, I want to draw out for you just an example of what you would see for a small, medium, and large effect size. So obviously I've shown you Statorade as a small effect size, or ridiculously small effect size, even if it's statistically significant. Now, for me to find statistical significance or a p-value less than 0.05, when there's such a small, minuscule difference between my comparison population, water, and Statorade drinkers, I'd have to have an enormous N size. So I'd have to be testing thousands of people to find a milliliter difference in their hydration. It would really be a difficult process to take. So again, that's why you're not looking for a lot of type of, when people do statistical testing on psychological things, they're not looking for small effect sizes. They're looking for like medium to large effect sizes. So what might that look like? Let's forget Statzerade for now, and let's think about what these different effect sizes might look like. All right, if you had a large effect size, then there wouldn't be much overlap at all in these populations. So you can see, here's this population, and then here's this population. So there's a very large effect size between the green and the dot and the solid blue. These two populations have a wide disparity between their means. That would be one of these very large size effect sizes. If I had a different group and I said I compared this population, I'm not sure if you guys can see that. This population to say this population, then you'll see that their means are much closer. These means are farther apart, these means are closer, and again, as we saw in like the Statzerade, the two population means are almost the same thing. So there's small effect size, medium effect size, large effect size, just like pizzas that you order at the Pizza Hut. All right, that's effect size. Next, on to power. Statistical power is the probability that a study will find a significant result if, in fact, the research hypothesis is true. This is a weird thing because how would you know reality, right? That's the strange part of power, is you're going to have to do a bunch of assuming here in order to find out what the probability of detecting a difference in the independent variable makes on the dependent variable, if it's true. You're going to really have to stretch a bit here to kind of get to power, but statistical power is a great idea, specifically if you realize your experiment has no power, and there's no probability that you would reject the null hypothesis, even if it was false. Then you don't have any power and you shouldn't be doing your study. You should be working on methodology to make sure that it's ready to have more power so that you have some discernibility of if there is a difference here that you'll find it. Okay, so how do you find the information you need to estimate power. Again, this is going to be power estimation. You're not going to find power. It's not like, oh no, I have a 50-50 chance of finding an effect of the independent variable if one exists. You're not going to know that. What you're going to have to do is gather the mean and standard deviation of population 2 and the predicted mean of population 1. What's the predicted mean? That's the thing I'm talking about here. You're going to have to make a bunch of assumptions. So power is it's an important concept theoretically, but what is it is going to change based on people's subjective opinions of the projected or predicted mean of population 1. Okay, so let's say we have some consensus. Sorry, my battery died as I was ranting about my problems with power. Okay, as I was suggesting, the problem I have with power is that when we predict power, we are making assumptions about the population mean for group 1 that we don't know. But when we come across, let's say we have consensus on that mean for group 1, we then take that mean and we find what the cutoff score would be that's necessary to reject the null hypothesis. Then what we'll do is we'll make a comparison distribution, and we'll take the z-score cutoff point for whatever our alpha level is, and on the distribution of means for population 1, and then we'll use the normal curve table to figure out what's the probability of getting a score more extreme than that particular z-score, which is our cutoff. There are several influences on power. One of them is effect size. The difference between the populations might mean that, look, if I'm trying to find a small effect size, my power is going to be hugely influenced by my n size. But if I'm trying to find some giant effect size, I'm not going to need a very large sample size to find that. The population standard deviation is something else that might affect the power that I have. So if the population standard deviation, we're assuming something that's called a homogeneity of the variance. And that big assumption, these big words, means the two populations that we're comparing, my sample and the population it's projecting, and the comparison population, we're assuming they have the similar variability between them. And then finally, figuring power from predicted effect size, you can take the mu for group 1, that's the average, and it will equal the mu for group 2 plus the effect size calculation, or Cohen's d, times the variation. All right. So that's all you guys need to know about power, is that it's the probability of detecting an effect of the independent variable on the dependent variable if one exists. Power in relationship to type 2 errors is an interesting concept, because if there's an effect of the independent variable, you either detect it or you don't. The probability of detecting it's called power. The probability of missing it is called beta. So we know that the relationship between power and beta is always such that they're going to equal 1 when they add them together, right? Because either you're going to detect an effect of the independent variable or you'll miss it if there is an effect of the independent variable on the dependent variable. So that's all I got for you on power. I hope this confusing topic is now a little less confusing for you.